Hello everyone, it's lecture number 2, right? Just to remind you people के आपको याद रहे आसानी से. Okay, so lecture number 2 is about VBT, right? And VBT is valence bond theory. First, because previously we have discussed about the coordination complexes, so we are considering the VBT for coordination complexes. Either we have a VBT for normal complexes, normal compounds as well, right? Uh, we need to consider certain examples, right? The first example that today we are considering is cobalt with 6 amines, right? And the overall charge is 3 plus, right? Okay. Step 1 is to consider the charge value over the math line. This particular formula is given by me. You need to draw the structure of it and all, right? So this is the first example. Okay, so previously you see the cobalt belongs to which system? D7. Okay, keep it in your mind. And now it is having 3 plus charge. How you will get 3 plus of it? You need to find out the oxidation state of your metal. This is very much important. So step 1 is to determine the oxidation state of metal. Ammonia is a neutral ligand. Before starting this, you need to consider the ligands, right? We have 3 types of ligands. Number 1, negative ligands. Number 1, positively charged ligand, and number 2 is neutral ligands, right? This is the one way to categorize the ligands. The other way to categorize ligands, it could be strong ligand or weak ligands. Weak, right? So they could be strong or weak ligand. In a VBT, the strength of ligand is very much important, and ammonia is a weak ligand. What is the difference between weak and strong ligand? I will explain in a while. Okay, in this example, you need to consider the oxidation state. Ammonia is a neutral ligand, right? So in terms of charge, it's a neutral ligand, so it is having 0 charge, right? So overall charge on the complex is because of this metal, right? So this plus 3 charge is all because of metal line, right? We can take any other example like iron with 6 fluoride is having 3 minus. This fluorine is having minus 6 charge because in a single fluorine we have -1, so it's a negative ligand actually, right? So it is having -6 charge, and the overall charge is -3, so the iron should contain +3, right? So oxidation state of iron is +3. So we need to consider the oxidation of metal at first step to draw the structure, the VBT structure of a complex, right? So we have 6 amino, right? Okay, now the step 2 is you need to write the electronic configuration of it. Electronic configuration के लिए what you need to consider, like cobalt belongs to atomic number 27, I guess. Yes, right? So 27, so it belongs to 3d7 4s2, right? 3d7 4s2 3, like, okay. What you need to do, because in a d orbital we have 5 suborbitals, 1 2 3 4 5, right? And then 4s, you need to label it. It's 3d and here we have 4s, right? How many electrons in 3d? 1 2 3 4 5 6 and 7, and then we have 2 electron in 4s. Done. Okay, the next step is you can use the back side of it. Okay, the next step is, a metal is having +3 charge, so you need to remove the 3 electrons, right? In the previous side you see the 2 electron from 4s and the third electron from 3d, right? They just remove because our metal is having +3 charge. Once we are left with the, because there is no more 4s, 1 2 3 4 5. So you see 4s is gone, right? You're supposed to write it again, right? So and we'll have, here we have dc7 because we removed the one electron from 3d, so it become 3d6, right? So it means we have now 6 electrons in 3d. Done. Okay, so next, just check out our ligand. Our ligand is ammonia, right? If you consider strength, so ammonia is a weak ligand, right? So weak ligand is, what is the difference between strong and weak ligand? If we have a strong ligand, then what will happen? Let's assume in this particular situation, if the strong ligand is present, like you can take the example of cyanide. Cyanide is a strong ligand. Okay, I'm telling you the situation in a, you know, in a both ways, like if we have weak or a strong ligand. If we have ammonia, then it will left with the same situation because it cannot compel the metal electrons to pair up. But if we have a cyanide, it's being strong ligand, what it will do, we have 1 2 3 4 and 5, right? And we have 6 electrons. 1 2 3 4 5 6, right? If cyanide is there, if cyanide approaches the metal ion, right, it will compel the metal electrons to pair up. We have total 6 electrons in d, so all the 6 electron will pair up. This is forced by the strong ligand, right? The strong ligand can pair up the electron while the weak ligand is unable to pair up the electrons, right? Ultimately, what will happen, you see the first example, like we will continue with our first example of cobalt with 6 ammonia, right? Okay, so here is the situation of cobalt, right? You can rewrite the structure. uh, 1 2 3 4. So we have 6 electrons. Being weak ligand, ammonia cannot pair them up, right? Next to 3d we can have 4s, and then next to 4s we can have 4p, and then we can have 4d, right? Because we have 6 ammonias, so we need 6 places. Every single ammonia, one ammonia will bring 2 electrons, right, or a pair of electron. So every ligand will bring a pair of electron with it, right? So because we have 6 ammonia, so one will bring 2 electrons, so in total we have 12 electrons to accommodate, right? In every subshell we have tendency to put 2 electrons. 1 2 3 4 5 6 7 8 9 10 11 and 12, right? You see, we have occupied the 6 subshells because we have 6 ligands and 12 electrons are filled there. 1 2 3 4 5 and 6. Now you check, okay, what kind of a hybridization we will have in this geometry, in this compound. We are using 1s. We are using how many p's? 1 2 3. We are using 3 p's, and we are using how many d's? 1 and 2, 2ds. So the hybridization would be sp3d2, right? So this is the hybridization of this particular complex. When we have sp3d2 hybridization, so our geometry is become octahedral, right? And I told you how to draw octahedral, right? So if you just turn it around, if the cobalt is in the middle, then we have 6 ammonias attached with it. In this way it is making octahedral, right? So मैंने उसको ज़्यादा complex नहीं किया, but you can also draw it like that to make it a complete octahedral. Okay, this is the geometry. This is the hybridization geometry. And what else we will get through it, that it is a weak ligand and it's a neutral ligand. Neutral ligand affect the oxidation state of metal, and the strong and weak ligand can pair up and cannot pair up the electrons of metal ion, right? And one more thing, if we have yes, through VBT we can also calculate the spin quantum, right? What is the spin quantum? Through the unpaired electrons of metal, ligand electrons are always paired, right? So we're just left with the option of metal's electrons, right? Either they could be paired up or unpaired, right? If they're unpaired, then you need to consider its spin value. For a clockwise rotation, we have plus half. For anti-clockwise rotation, we have minus half value, right? And when we have a pair of electron, right, in a single box, plus half, minus half, they both cancel out, we're left with zero spin value, right? But if we have like situation like this, like in cobalt, there are four single spin electrons, right? So it's become plus half, minus half, yani zero. So we have plus half, plus half, plus half, plus half. So how many plus half? You cannot write it half is equals to 1 and half is equals to 1, so it's become 2. No, it's like plus 4 by 2, right? So the spin value for this particular compound is plus 4 by 2, right? So it's a high value, so it's a high spin compound. Similarly, certain compounds are low spin, right? If somebody is using, you know like when we have drawn the structure, like these are the metals, then 4s, then 4p, and then 4d. If somebody is using 4d, right, this is the 3d. If any compound is using inner d, so we can call it as it's inner d complex, right? When it is using outer d, right, it's outside, it's become outer d complex, right? So there are two kind of complexes, outer D or inner D complexes. So right now in this current situation, it is a outer D complex because we are using 4D, not 3D, right? Thank you.